Good afternoon, class. Here's an exam for review, part 3, covering sections 5.2 and 5.3. 5.3, the definite integral. 5.3, FTC, the fundamental theorem of calculus. Suppose a continuous function f is defined on the interval of 2. The interval is divided into n subintervals. Delta x equals b minus a over n. And x sub 0 is a, x sub 1 is a plus delta x, all the way to x sub n, which is a plus n delta x. This would be a, this would be b. A Riemann sum associated with f is the following sum. The definite integral of a to b f of x dx, which is a number, by definition is equal to the limit of this Riemann sum, summation of f of x by delta x as I goes from 1 to n, as n approaches infinity. Now this part is the same as this part, which is f of x sub 1 delta x all the way to f of x sub n delta x. But we have to take a limit of that, where delta x defined as b minus a over n, and x sub I is a plus I delta x, and x sub I is any point in the subinterval of a sub I minus 1 and a sub I. As you recall, we looked at the left endpoints, the right endpoints, the midpoints. None of them matters because it's an approximation and it becomes exact when we take a limit. So let y equals f of b a continuous function, f of x, let y equals f of x be a continuous and non-negative over an interval of a to b. Definite integral is the limit as n approaches infinity. Equivalently, you can say delta x approaching 0. Of the Riemann sum of the areas of rectangles under the graph of y equals f of x over the interval of a to b, and that is the precise definition of the area under the curve, as long as the function is continuous and non-negative. Otherwise, it becomes the difference of areas. First, let's explain what this is by looking at every part of that, starting with this integration symbol. The symbol, which looks like an S, was introduced by Leibniz and is called an integral sign. It is an elongated S and was chosen because an integral is a limit of sums. A is the lower limit of integration. B is the upper limit of integration. F of x is called the integrand. And dx, we call it a variable of integration, also known as a dummy variable. Why is that? It is called a dummy variable because the answer doesn't depend on the variable chosen. The dx simply indicates that the independent variable is x. The integral of a to b f of x dx is a number. It doesn't depend on x. We should use any letter in place of x without changing the value of the integral. For example, the integral of a to b f of t dt or f of x dx means the same thing. Or its approximation. The approximation is the Riemann sum, the summation of f of x sub I delta x as I goes from 1 to n, which is f of x sub 1 times delta x all the way to f of x sub n times delta x. This sum is called a Riemann sum. The precise value is when we take a limit of this as n goes to infinity. We want to express this expression as an integral on the interval of 0 to pi. Recall, we are saying the integral of f of x dx as it goes from a to b is the limit of this Riemann sum as n goes to infinity. So that represents the area under the curve as long as it's non-negative and it's continuous. So first and foremost, let us compare. So we are going to put this next to it. So compare these two. clearly a and b means 0 and pi. So a is 0, b is pi. But if you compare this is delta x, this is f of x sub I. So if this is f of x sub I, f of x must be x cubed plus x sine x. We've already discussed the interval of a to b, a to b. And so therefore, this is this integral, the integral of 0 to pi, a to b, f of x, which is x cubed plus x sine x times dx. Remember, delta x is replaced by dx. So compare and come up with the answer. We want to express as an integral on the interval of 0 to 2 pi. Obviously, this is a, this is b. And we are going to compare. So AB. Delta x is b minus a over n. Two pi minus 0 over n. X sub I is a plus I delta x. Replace the a with 0. Basically, that's nothing. I times delta x, or 2 pi over n, or 2 pi I over n. So f of x sub I is this. This is f of x sub I. So f of x must be sine x in the interval of 0 to 2 pi. Again, all you have to do, replace this with this, and it gives you back. So this is the reverse process, everybody. So the integral of f of x, which is sine x, dx from a to b, 0 to 2 pi. So pretty straightforward, everybody. Use summation formulas to compute this. The integral of 0 to 2, 1 minus x squared dx. And we remember that the integral of a to b f of x dx is this limit. Now, using the limit, as we did it with differentiation, that's the start, everybody. And that is pretty tedious. I want you to know that. Ultimately, we take the easy way out, which is the FTC, fundamental theorem of calculus. Okay, we will use that later on, but for now, we are going to use that just to get us started, everyone. So this is the function f of x. From 0 to 2a, 0, b is 2. So that's to get us started. Delta x is b minus a over n. So 2 minus 0 over n. X sub I is a, 0 plus I times delta x. So it makes it 2I over n. We want to evaluate the limit here. So for now, let's just go with the summation. Let's look at the summation, and then we take a limit finally. So first, let's simplify this part, everybody. First, let's write it and simplify it. So summation of f of x sub I 1 minus x sub I is 2I over n, quantity squared, and then times delta x 2 over n. So I want to write this expression in essence, okay? I want to write this expression. So there we have it. Let's raise this to the power of 2, gives us 4I squared over n squared. Let's distribute here, we get 2 over n. Let's distribute here, we get 8I squared over n cubed. Okay, so I believe it's pretty straightforward. We are going to put that in a format such that this can be used. So what do we have here? Summation of 1. If we go back to summation, some of the summations that we have seen, the formulas in algebra, summation of 1 is n as I goes from 1 to n. Summation of c is nc as I goes from 1 to n. Summation of I is n times n plus 1 over 2 as I goes from 1 to n. Summation of I squared is n times n plus 1 times 2n plus 1 over 6 as I goes from 1 to n. Summation of I cubed is n squared times n plus 1 quantity squared over 4 as I goes from 1 to n. So we are going to separate this such that it has 1, c is a constant like 5, 2, whatever, I squared or I cubed. So look at this one. I can write it, bring the 2 over n out. So I'm going to make up 2 summations. This one and the summation for that. This one is 2 over n summation of 1. This one is 8 over n cubed summation of I squared, of course, with a negative sign. So this part, again, I want to make sure we understand that this part is this one. This one with the negative sign is this. So I want to be absolutely clear as to what's going on, everybody. Very straightforward. Now we are ready to replace the summation of 1 with n, the summation of I squared with n times n plus 1 times 2n plus 1 over 6. Let's do that. Remember, we want to take a limit. So we are interested in the first step. So first and foremost, this will simplify to 2. This one, the denominator is 6n cubed. I want you to pay attention to the numerator. N times n squared times 2n. 2n cubed times 8 is 16n cubed and a bunch more. Now, what happens is it is important to understand that the product of these pieces is 8n cubed, and then the rest of them go down in order, descending order of n. The reason I'm not interested in the rest of them, because we are going to take a limit 8 times, my apologies, this is 2 times, this is 2 times 8, which gives us 16. Now, this integral is the limit of this one. So the limit, we have to take a limit as n goes to infinity. So first I simplify, now I take a limit. This becomes 2. This one, as you recall, because they both have the same degree, the answer would be 16 over 6. So 2 minus 16 over 6. And that is negative 2/3, because twelve over 6 minus 16 over 6 is 4 over 6. Negative divided by 2, negative 2/3. So it becomes negative 2/3. Everybody, again, I think it's pretty clear and pretty straightforward. We're going to move on. So we went through the process of limit to find this. Now, in this example, we want to evaluate the Riemann sum for f of x equals x cubed minus 6x, taking the sample points to be right endpoints, and a is 0, b is 3, and n is 6. In part B, they want us to evaluate this. Now, what happens is, where we go through this process, it's an approximation of that. For this one, we're going to use the limit. So first and foremost, we want n equals 6. This is the graph, everybody, and we want to go from a equals 0 to b equals 3, 1, 2, 3. So in essence, we want this shaded region. I'm going to clean it up. So this shaded region, and it's important to understand that when we go through the process, because the function is not positive, it's the difference of areas. In other words, this part is considered positive, this part is considered negative. Clearly, this is larger than that. The result, I don't know what the answer is, but I should know it's negative, roughly. All right. So first and foremost, what is my function? F of x is x cubed minus 6x. What is my a? 0. What is my b? Is 3. So we can calculate delta x as b minus a over n. In this case, n is 6. So 3 minus 0 over 6. And we get 1/2. Okay. X sub I x sub I is a plus I delta x. We're going to use it for the next page. But for now, what I want to do, I want to show you the easy way out. As I mentioned, this one, I'm going to put a line segment that goes from 0 to 3, and I'm going to expand it so it becomes easy to work with. This is much larger than that for the sake of illustration. So this is 0 or a, this is 3 or b. And I'm going to cut it into 1, 2, 3, 4, 5, 6, n equals 6 pieces. So when I divide, I get 0.5 or 1/2. So 0.5, 1, 1.5, 2, 2.5, and equals 3. Now, what do we want to use? Want to use the right endpoints, everybody. Since we want to use the right endpoints, ignore the first point. So basically, ignore this one. Ignore this one. So we want all of those, which means I want R sub 6 using this formula. Delta x is fixed as 1 over 2, and then the height would be f of 0.5, f of 1, f of 1.5, f of 2, f of 2.5, f of 3. We don't have the first one because we are using the right endpoint. So you really have over here this part, this part, this part, this part. So for this one, for example, this would be just roughly, I'll show you just two of them. The last one is easy to see. This is almost half. So this would be the rectangle with the height being f of this point or f of 3, okay? And this one is 0.5. Is this one, and this is 1, for example. So on and so forth, okay? So I just wanted you to see that. Looking like that. Let me erase my mess. So it looks like that, okay? So 1/2 times f of 0.5 plus f of 1 all the way to f of 3. Now, just as an example, I'm going to show you one of them. If I calculate f of 1, it's 1 because that's actually easy. So what is f of 1? That would be 1 cubed minus 6 times 1. Okay. If I want f of 3, would be 3 cubed minus 6 times 3. Okay, and so on and so on. We end up with negative 3.9375. And note this value represents the difference of areas. That's why it's negative, everybody. That's why it's negative. All right. Now we actually want to evaluate this, which means we want an exact answer, which means we have to go with the limit of the Riemann sum. So to do that, the delta x is no longer b minus a divided by 6, but rather divided by n. Okay. So this is again the same area we are talking about. Okay. So now this time actually we will get this exact area. Okay, exact area. So we have the function, we have the a, we have the b, and delta x is b minus a over n, not 6. And it becomes 3 over n. X sub I is a, which is 0 plus I times delta x, so 3i over n. So the integral is the limit of the Riemann sum. And f of x sub I, we are going to replace it with 3i over n and delta x with 3 over n. So what is f of 3i over n? So basically, this is your function x cubed minus 6x. So 3i over n to the third minus 6 times 3i over n times 3 over n. And by the way, you can simplify this expression. Remember, we want to simplify this expression. And when we simplify it completely done, then we take a limit. So I'm not going to carry the limit. I'm going to just simplify that. First, let's plug in. And 3 over n, we put it in the beginning or at the end, makes no difference, okay? So this one is 27 I cubed over n cubed. This one is minus 18 I over n. So this part, 3 times 27 is 81 over n to the power of 4 I cubed with the, okay, so this part only, okay, is 27 over n cubed. 27 times 381 over n to the power of 4 I cubed. Now this part, 3 times 18 is 54, so minus 54n squared summation of what we are doing. Again, take a look at here. We want to have 1 or c or I squared or I cubed, because this summation, we know the answer. This summation, we know the answer. We are going to replace this summation with n squared times n plus 1 quantity squared over 4. And this summation, we are going to replace it with n times n plus 1 over 2. Okay. This integral is the limit of this expression as n goes to infinity. Now, for this expression, class, this denominator is 4 n to the power of 4. This one, I hope you see that this gets squared up, and this is n to the power of 4, and then it's in descending order. N squared, actually this is easy to see, the next one is n, but even if you don't write, they go down in descending order. So for this one, we are going to have 81 n to the power of 4 in the numerator plus bunch more. The denominator is 4 n to the power of 4 minus 54 n squared. Actually, that one is plus 54n, but it doesn't matter. The denominator is 2n squared. And this is what we have. Okay, so that's a negative sign. The highest degree term is n to the power of 4 for the top and the bottom. So the answer is 81 over 4 minus the highest degree term for the top and the bottom is n squared. So minus 54 halves. And when you do the math, you end up with negative 27 over 4, because this one is minus 108 over 4. So 81 minus 1, which is minus 27. So as you can see, we can do it by the Riemann sum. Now, use the signed area interpretation of the definite integral to compute the integral of x dx from negative 1 to 2. So what is the function? The function y, or f of x, is x in the interval of negative 1 to 2. And f of x equals x, or y equals x, is a line through the origin. We want to go from negative 1 to positive 2. That means we want this area, we want this area. The difference is the answer. To find the difference of the areas, each one is a triangular shape, so we can use the formula A is 1/2 base times the height. So for the green one, this one has coordinates 2 and 2. Therefore, this distance is 2. So is this distance. So the area is 1/2, 2 times 2, or 2. For the red one, this has coordinates -1, -1, which gives us the distance of 1 here. distance of 1. So that's why positive half of 1 times 1 is 1/2, and their difference is 3/2. And we are done. What I'd like you to do is at home show that this, the integral of -4 to 1 6x dx is -45, and here's your function. Also, I want to quickly show you this concept, which is known as the FTC, and what it says. If you want to evaluate this, you can use FTC, and the advantage of that is if the area fails, this won't fail, because this is a shape that you are familiar with. But if you are not familiar with the shape, how do you do that? Then you use the FTC, or you have to do with the Riemann sum and taking a limit which takes forever. So here's the function we are interested in. The antiderivative is 1/2 x squared. Because I'm evaluating from A to B, namely -1 to 2, I don't need a constant because the constant will go away. And so 1/2 x squared 2 squared minus -1 squared. And I hope you see this is 3/2. We will elaborate on this shortly as far as the definite integral is concerned and using the FTC. Here's another example. We want to use geometry to evaluate this. The square root of 9 minus x squared, take the integral from -3 to -3 to +3. So square root of 9 minus x squared dx. To come up with the answer, we need more calculus. So we discussed this concept in calculus 2. But for now, we're not going to discuss calculus 2. Rather, we're going to discuss area. It's easy to see the function g of x is square root of 9 minus x squared. We want it over the interval of -3 to 3. And if we recall the equation of circles, okay, centered at 0, 0, x squared plus y squared is r squared, or x minus h quantity squared plus y minus k squared equals r squared. Now that we remember those, okay, so that's the general form. What I want you to concentrate on, if instead of g you call this y and then you square it, you get x squared plus y squared equals 9 squared, because you get, if I square it, y squared is 9 minus x squared. And this is a circle centered at 0, 0 with the radius 3. So what is the graph? The graph looks like that is a semicircle of radius 3. Therefore, pi r squared is the area of a circle. Half of pi r squared. So circle, and we want half of that because it's a semicircle where the radius is 3. So 9 pi over 2 is the exact answer. And for this, again, you cannot use calculus 2. We are using the area. Some properties of definite integral. If you have a point, that means the integral of a to a f of x dx is 0, because it's delta x in essence is 0. If you have a point, it doesn't cover an area. Number 2, the integral of f of x plus minus g of x dx, as it goes from a to b, we can cut them into 2 pieces as we did with the differentiation. So simply put, if this is f of x, this is g of x, this one is the area under the curve for this one, assuming both of them are positive. This is the area under the curve for the g of x. So if you put them together, it goes up by this much. So you add them up, so geometry can show that. Scalar rule, if we multiply it by a number, we can take it out. So this is f of x, this is like 2 times f of x, okay, in the area under the curve. Dominance, if f is larger than g from a to b, then the integral of f of x dx from a to b is larger than or equal to the integral of g of x dx from a to b. So f is at top of g from a to b. Doesn't matter what happened afterwards, before a and after a, or after b. Just from a to b, then therefore this is larger than this because it covers the area under the curve. And we are assuming we are dealing with a positive function for now. Bounding, if some number m, lowercase m, is less than or equal to f of x, and f is less than or equal to capital M, again from a to b, then when we multiply by b minus a, both all sides in essence, that works out the same, because this is really the same as multiplying by b minus a. So here's the minimum value of the function. If you look at this function, the minimum value is here. So you draw a rectangle. And the maximum value of the function is here. You draw a rectangle. Obviously, the green rectangle has an area less than this blue area, contains this green one also. And this almost yellowish color has all the area from here down. Splitting additivity, if you are taking the integral of a to c f of x, the same as a to b f of x dx plus b to c f of x dx. Notice these two must be identical. And then from here, let me use a different color. From a to c. So be careful with that. So basically, this is from a to b, this is b to c. You can say it's from a to c, assuming b is between a and c, and it really doesn't have to be. Opposite rules, the integral of a to b f of x dx is minus the integral of b to a f of x dx. A constant, if you have a c, just the integral of a to b c d of x, because this will give you cx from a to b, so c times b minus a. Non-negativity, if f is positive, as x goes from a to b, this integral must be positive. All right, now we know that the integral of f of x dx, when we go from 1 to 3 is given as 6, 3 to 7 is 9, 1 to 3 is negative 4. We're going to evaluate the following. So the first one is 1, 2, 3 times 3. So just multiply this one by 3. And you get 18. I think pretty straightforward. Just multiply it by 3, and there you have it, everybody. Uh, 2f of x minus 4g of x. So take the 2 out, take the 4 out, and rewrite it in the following manner. We know this one is 6, replace it, minus 4. We know this one is negative 4, replace it. So 2 times 6 minus 4 times minus 4, and of course 12 and 60. The integral of 1 to 7 f of x dx. So let's look at what we can do here. This is 1 to 3, this is 3 to 7. So 1 to 7, this one plus that, right? Notice the intermediate one is the same, the beginning to the end, 1 to 7. So this is 6, this one is 9, they add up to 50. 3 to 1. Well, if 1 to 3 is this, 3 to 1 is the opposite of that. There you have it. I think it's very straightforward. Everybody should pay attention to this basic rules. There is really not much to it. Okay, everybody. And that's all there is to it. FTC. The fundamental theorem of calculus is appropriately named because it establishes a connection between the two branches of calculus, differential calculus and integral calculus. And everybody remembers the area under the curve. It gives the precise inverse relationship between the derivative and its integral. The ddx, the derivative of the integral of a to x f of t dt is f of x. In other words, whatever this one is, this is a number, and this is the variable that will replace the t. Because first you have to integrate this, then you have to differentiate. So in essence, they undo each other. Differentiation and integration, they undo each other. So the FTC theorem of calculus. Suppose f is a continuous function in the interval of a to b. If g of x is the integral of a to x f of t dt, okay, then g prime of x must be f of x. If the integral of a to b f of x dx, then capital F of b minus capital F of a represents this, where capital F prime is lowercase f. That's the same thing. So in short, the integral of a to b f of x dx, which is the definite integral, which is a number, find any antiderivative and evaluate it at the endpoints f of b minus f of a. Their difference, the answer. The derivative of the derivative of the integral of a to x f of t dt is f of x. To integrate this from 0 to 1, it's a definite integral. The answer is a number. So this gives you 1 over 8 x to the power of 8. We don't need a constant. We plug in 1, we plug in 0, and we get 1 over 8 times 1 to the power of 8 is 1, 0 to the power of 8, 0 is 1 over 8. And here's the tip. Even if we use another antiderivative, capital F of x plus c, in the evaluation theorem, the result will be the same. Capital F of b plus c minus capital F of a plus c, these two cancel each other, we get the same thing. That's why we don't need to write a constant. The integral of 1 to 2x to the power of minus 1 dx, first and foremost, I want you to notice this is the same as 1 over x. Therefore, it's a natural log. So it's ln2 minus ln1. And as you know, ln1 is 0. And ln2 is the answer, which is an exact answer. In calculus, we keep the exact answers, everybody. If we didn't use the absolute value, it wouldn't make any difference because the lower limit and upper limit are both positive. But I'm using the same question with different limits. But now we must use the absolute value, because if we don't, ln of -1 is not defined, because the domain is from 0 to infinity for natural log. So we must use the absolute value here. So as you can see, this is ln1 minus this is ln2. And again, ln1, you know it to be 0. So negative ln2 is the precise answer. The integral of 0 to pi sine x dx. The derivative of sine is cosine, but the integral is negative cosine x. I'm going to keep the negative sign out, and I'm going to put the upper limit first, pi. So cosine of pi minus cosine of 0, and I keep the negative sign out. You know cosine of pi to be -1 minus cosine of 0 is +1. So this is -2. The negative outside makes it positive. We had done this before. We found the antiderivative. We didn't evaluate it. In this case, of course, because this is t, you want to be careful so we don't get x. We get t plus sine t. The derivative of cosine is negative, but the integral of that is positive sine t. And we're going to put the upper limit first. So power 2 plus sine of power 2. Then we put the lower limit. As you can tell, 0 or sine 0 makes no difference. Both of them are 0. Power 2 plus sine of power 2 is 1. And we keep it as such because it's an exact answer. Well, just with the differentiation, first we are going to write this one as x to the power of 1/2, and this has exponent 1. 1 and 1/2 gives us exponent 3/2. So 5x to the power of 3/2 plus 3x to the power of 1/2 dx. Now we can use the power rule. 5 divided by 3/2 plus 1, x to the power of 3/2 plus 1. 3 divided by 1/2 plus 1, x to the power of 1/2 plus 1. And believe it or not, this is the only calculus step. You put an asterisk next to it. And you're done. Now let's do algebra. We plug in 4, 1, and so forth. And as you can see, this is 5/2. So this is 2, 3/2. This is also 2. Plug in 4, evaluate it, minus, plug in 1, evaluate it. So when we plug in 4, 4 to the power of 5/2 means square root of 4 to the power of 5, which means 2 to the power of 5, which means 32, which means 2 times that is 64. 4 to the power of 3/2 means square root of 4 cubed, but this is 2, 2 cubed is 8. 2 times 8 makes it 16. 1 to the power of 5/2 or 3/2 makes no difference. They are 1. So 2 and 2 is 4, so minus 4. And they give us 76. We want to evaluate the integral of f of x dx from -2 to 2, where f of x is defined as 2 when x is between -2 to 0 and 4 minus x squared when it's from 0 to 2. Therefore, this has to use this function, which is piecewise defined function. So we use the 2 from -2 to 0, and then from 0 to 2, we use 4 minus x squared. It's important to understand what happens here, everybody. Okay? The two pieces. This is very straightforward. 2x from -2 to 0. This is 4x minus 1/3 x cubed. So, by the way, even if it was from -infinity to 0 and 0 to infinity, we would use exactly the same. Okay. So that will give us the same thing regardless. That's important to understand. So as I mentioned, 2x, and this one is 4x minus 1/3 x cubed. So again, let me put the asterisk next to it. This is the only calculus step. Now plug in. So what do we plug in? First we plug in 0 minus, then plug in -2. This one first plug in 2, then plug in 0. So this is the evaluation, everybody, which we're going to look at in a moment. Let's see what we have here. This is 0, don't worry about it. This is positive 4. This is 8. This is minus 8/3. This don't worry about it. This don't worry about it, right? So what we have is 4 plus 8, 12, minus 8/3. And 12 is 36/3 minus 8. 36 minus 8 is 28. So 28/3. Very straightforward, everybody. All right, we are going to move on. G of x is given as the integral of 0 to x 1 plus t squared dt. And we want to find the derivative of the function. And I'm going to show you this FTC we are going to use. We can use that if we are dealing with a continuous function, and f of t, which is the square root of 1 plus t squared, is a continuous function. Why is that? Because when you have a square root, it must be, what's underneath must be larger than or equal to 0. As you know, this is always positive because it's 1 plus t squared. And therefore, it's continuous everywhere from negative to positive infinity. Therefore, according to fundamental theorem of calculus, all you have to do, replace the t with x. So g prime of x is the square root of 1 plus x squared, according to this FTC. So this says if the bottom is a number, whatever it might be, and you want to take a derivative of this expression, just replace the variable in there with the x. d dx of the integral of 1 to x squared sine t dt. We want to take the derivative of this expression. First, the function f of t sine t. Then I'm going to remind you the derivative of a to g of x f of t dt. If this is x, we have the basic FTC and we're fine. But if it's a function of x, you have to replace the t with g of x and then times g prime of x. This is by the chain rule. So I'm going to show you two ways on this one so you've been exposed to that. First and foremost, just following that, replace the t with g of x, x squared. So your g of x is x squared. So sine of x squared, and then the derivative of x squared, which is 2x, just following this formula. And of course, we put the 2x in front. I'm going to show you a second method just for the sake of argument, and that means we are going to integrate this first, then we take a derivative of that. So the derivative We want the derivative of the integral of this. So what is the integral of sine? Minus cosine t evaluated from 1 to x squared. Please understand what I have here. What I have here is this. The integral of sine t dt from 1 to x squared. Sine gives you negative cosine t from 1 to x squared. So first we're going to put x squared, and then we're going to put 1. So never mind the differentiation yet. Let's evaluate this. So minus, I can keep the negative out, cosine of x squared minus cosine of 1. Now I want to differentiate this term by term. The first one, what is the derivative of cosine x squared? Is negative sine x squared times 2x. This negative, I'm going to keep it outside. This negative, I'm going to keep it outside. So cosine gives me negative sine x squared times 2x. Cosine 1 or cosine 5 or cosine of 2 pi over 3. This is some number. The answer for this one is 0, everybody. So again, this gives you 0. Cosine x squared gives you minus sine x squared times 2x. This negative sign remains. And I hope you can see that this is the same as this expression. So we prove both ways. So we prove using the formula that we have here. And let's say we don't have that formula, we don't remember it, just integrate it and then differentiate. The advantage of this formula is if you have an expression that you don't know how to integrate, then you better stick with the theorem here. That's the theorem. So again, in short, if you're taking the derivative of the integral and the bottom is a number, the top is x, you just replace it with the variable. But if the top is a function of that, you replace it with that top function and then times g prime by the chain rule. What about here? In the same manner, notice your function is tan t, everybody. So we're going to replace the t with this upper function x squared plus x. And then by the chain rule, time its derivative, which is 2x plus 1. So tan of x squared plus x. And then the derivative of that, 2x plus 1. And normally we put that in front. Again, very straightforward. Now we have two functions with the lower limit as well as the upper limit are both functions. When the upper limit is a function, we have f of g of x times g prime of x. What happens when the bottom is, then we expand it in the following manner. First of all, the function is t squared. Then we use this formula. If we are taking the derivative of f of t dt as we go from g to h, then if f of the top limit times h prime of x minus f of the bottom limit times g prime of x. So let's do this step by step. F of t is t squared. So replace the t with sine. So sine squared x. That's this part. H prime of x. Then the derivative of that, the derivative of sine x, I mean, times cosine x. Minus f of g of x. So replace the t with tan x minus tan squared x. And then times g prime. Here's your g. So let me just write that in case. This is the h function. This is the g function. And g prime, the derivative of tangent is secant squared. And you can leave it like that, sine squared cosine minus tan squared secant squared, because it's as simplified as possible. Finally, here's the case, and you remember that we have this formula when the bottom is a number and the top is a function. It's the other way around. So we are going to write this as the same thing. We're going to interchange these two, and this changes to a negative sign. Okay, remember, f of t is this one, but we are going to put a negative sign, and we're going to take the sign as up and make it upper limit, 1 make it lower limit. This, we can use this formula. So we're going to keep this negative sign. 1 plus f of t is 1 plus t squared. So replace the t with sine squared. And according to this formula, I need g prime of x. I need the derivative of sine, which is cosine x. And now it's a good practice to put the cosine in front. And that's the final answer.